Hi guys, good morning. You're there. Yeah, he's there. Cool. Good morning, guys. Shall we start?
Yes, sir.
Yes. So we have completed your chemical bonding, right? So we will be seeing today, as you asked for it, we'll be seeing redox reactions, right? Just give me a moment. Okay. Right. Okay. So this is a very small chapter. Okay. We'll be requiring max 2-3 classes to complete this chapter. Right. Cool. Right. Okay. Let me start this chapter with a question. Okay. So, like I'm writing this reaction. I have C plus O2 giving CO2. Okay. This is a very normal reaction you would have been studying from your lower classes, isn't it? Right. Now tell me whether this reaction is a what to say an oxidation reaction or a reduction reaction.
Oxidations.
Hmm. Okay, that's what we have been taught, isn't it? From our lower classes, we said that this particular reaction was actually oxidation reaction. That's what we call it, right? But in reality, people, right? In reality, there are no reactions where you can have only oxidation, right? Or there are no reactions where you can have only reduction, right? All the reactions you're going to see in chemistry, right? All the reactions are actually going to be redox reactions. That means oxidation and reduction is going to happen simultaneously, right? So oxidation cannot happen separately, reduction cannot happen separately. In all the reactions, oxidation and reduction will happen simultaneously. If that happens, definitely this will happen, right? That is how the rule of chemistry goes, right? Okay. Now, how do I prove it to you? Right? How do I prove it that this particular reaction is not an oxidation reaction, but a redox reaction, that is reduction and oxidation reaction, right? Now, you can easily understand that carbon here, right, in the reactant side, right, didn't have any oxygen, right? But in the product side, carbon has attained oxygen, carbon has gained oxygen, right? So obviously, I say that carbon is getting oxidized, right? Carbon is getting oxidized, right? And if you look at oxygen, for example, if you take oxygen, right, I am saying that oxygen is actually getting reduced, right? Oxygen is actually getting reduced. Now, how will I prove it to you? Now, I'll not be able to prove it to you, right? Because we need to learn some concepts for us to understand how is it oxygen is undergoing reduction, right? But please trust me, right? Oxygen is actually undergoing reduction, right? By the end of this class, you will understand why and how oxidation is undergoing reduction, right? Okay. So coming to the point. So the thing is, I told you there will be no reactions where oxidation and reduction happen separately, right? It is always going to happen simultaneously. Both will happen simultaneously. Now let me give you a very better example, right? Okay. Let me take this. I have H2S plus Cl2 gives HCl plus S2. Okay. Right. Let me take this reaction, right? H2S is hydrogen sulfide reacting with chlorine to form hydrochloric acid plus sulfur. Okay. Now let me see what is happening here. Right. Now, if you look at here, now we will speak about two elements. Right. Now, please understand, people. Right. If I say redox reaction, right. Generally, what happens is one element in the reaction will get reduced, and the other element in the reaction will get oxidized. That's the general case. But there are cases, there are special examples of reactions where there can be only one element, right? That element itself will undergo oxidation as well as reduction, right? So again, I tell you, right? Generally what happens is there'll be one element in the reaction which undergoes reduction, and there'll be one element in the reaction which undergoes oxidation, right? But there can be special cases where only one element is there. I mean, there are many elements, but there is only one element which undergoes oxidation as well as reduction, right? So those kind of reactions are what are called as disproportionation reactions. But anyways, you don't have to worry about it. We'll see it later, right? So we'll concentrate on this example now. Okay, now let me concentrate on sulfur first. Right? Let me concentrate on sulfur first, right? Before this, we all know what are all the definitions of oxidation and reductions are, right? So let me just give a very quick recap of what you learned already in your lower classes. Then we look at this example, right? So when I say oxidation, right, how or not will you be able to define oxidation, people?
Gain of
oxygen.
Okay, correct. Gain of oxygen or removal of hydrogen. Okay, then in terms of electrons,
Gain of electrons.
gain of electrons. So if you
loss
say
of
that
electron.
it is going to be loss of electron, right? It is going to be loss of electron. Correct, right? So say it is exactly going to be opposite in case of reduction. So obviously it is going to be loss of oxygen, gain of hydrogen, or in terms of electron, it is gain of electrons. Right? Okay, fine. So this is enough for us to understand what is happening here. Right. So let me take sulfur, for example. Right. Sulfur was with hydrogen in the reactant side. Correct? Right? Sulfur was with hydrogen in the reactant side. But if you look at the product side, sulfur has lost hydrogen. Sulfur has lost hydrogen. So what is there? Loss of hydrogen is basically going to be oxidation. Right? So sulfur is the one which is getting oxidized here. Okay, right. Now let me look at chlorine. What is happening to chlorine? So chlorine in the reactant side had nothing, right? It was just chlorine. But if we go to product side, to chlorine, I have added a hydrogen, right? So chlorine has gained hydrogen. So I would say chlorine is the one which is getting reduced. Right? Chlorine is the one which is getting reduced. So you see, this is also a redox reaction where one element gets oxidized, another element getting reduced. Okay, now what is this loss of electron and gain of electron? For that also I'll give you an example, right? Okay, so there are so many examples. Let me take a very simple example, right? So if I say that sodium reacting with chlorine to form sodium chloride, right? I'll better write it as Na plus and Cl minus. Let me write it like this. Okay. So now what is happening here? Sodium, right? Sodium, what happened to sodium here? Sodium has lost an electron to form Na plus, correct? Sodium has lost an electron to form Na plus, right? So obviously I will say that sodium is the one which is getting oxidized because we just said now, oxidation is also a case where if the element loses electron, right, it is going to be oxidation. So you can see that sodium is losing electron, right? And what is happening to chlorine? Chlorine is accepting electron, is it not? Right? So chlorine in this case, what is happening? Say Cl2, half mole of Cl2, because there is only one Cl minus there, right? So half mole of Cl2 accepts one electron to form Cl minus, right? So now what is happening to chlorine? Chlorine is accepting electrons. So I would say that chlorine is actually undergoing reduction. Okay, right? So anyways, so these three are the one which we primarily studied, right? Gain of like in terms of oxidation, it is gain of oxygen or removal of hydrogen or loss of electron, and in reduction it is going to be opposite. Okay, right, fine. Why do we have this loss of electron and gain of electron? Is because oxidation and reduction need not involve oxygen and hydrogen in the reaction at all. Like just like you see here. Right, Na plus Cl2 giving Na plus Cl minus, right? You see that there are no hydrogens, there are no oxygens. So we need to give definitions of oxidation and reduction, even if you don't have hydrogen or oxygen in the reaction. That's the main reason this is also getting involved. That is, the electrons are also getting involved, right? And in the due course, well, when I proceed, you will understand that there will be one more way by which you will be able to define oxidation and reduction, right? So that will be in terms of something called as oxidation number. But before that, right, we will see certain definitions which you have to know. Right. So in any reaction, right, there will always be something called as an oxidizing agent, and there'll be something called as a reducing agent. As simple as that. Right. Fine. So we know what generally agents do. Right. Say for example, if I have an LIC agent, right? So what does he help? What does he do? Right? He helps in getting an LIC policy, isn't it? Right? And in biology, you would have studied about pollinating agents. What do? They help in pollination, isn't it? Same way, when I say agent in chemistry, it is going to help in something, right? And specifically, if I say oxidation, it is going to help in oxidation. When I say reducing agent, it is going to help in reduction, right? Now that is understood. Oxidizing agent is helping in oxidation. Oxidize is something else. That's what I need to say, right? And reducing agent is going to help in reduction. And basically, what I'm trying to say is, it is the one which is going to reduce something else. Okay. Now the next question is how, right? How is it that oxidizing agent is able to oxidize something else, and how is it that reducing agent is going to reduce something else, right? Is the question now, right? It is very simple, right? So please understand, it is going to be a sacrificial method. What do you mean by sacrificial method? I am going to sacrifice something from me so that the other thing is happening, right? So here also it's going to be same thing. So oxidizing agent is the one which is going to oxidize something else, right, by reducing itself, right, by reducing itself, right? Same way, if I say reducing agent is going to reduce something else, again by sacrificial method. Sacrificial method is something that is going to exactly undergo the opposite process. So since it is reducing something else, it will undergo oxidation, and there undergo reduction. It will undergo oxidation, right? So how will you find out in the reaction, right? In the reaction, if they ask you to find which is an oxidizing agent and which is the reducing agent, this is very simple. Whichever is undergoing oxidation is the reducing agent, and whichever is undergoing reduction is the oxidizing agent, right? So we took the example of H2S plus Cl2 giving HCl plus H2. In that case, sulfur was undergoing oxidation, right? So how will I call now sulfur? Sulfur will be my reducing agent. It is undergoing oxidation, so I'll call it as reducing agent. Same way, chlorine was undergoing reduction because I had addition of hydrogen there, right? So chlorine is undergoing reduction. So how will I call it? I'll call it as oxidizing agents. Okay, so this can also be questions, people. They'll just give you a very simple reaction and ask you to find the species which is getting oxidized, species which is getting reduced, oxidizing agent, reducing agent. All these can be asked, right? And you know how to answer them. Whichever is undergoing oxidation is my reducing agent, and vice versa, right? Okay, so these are the simple things which we have to know, right? Now moving on, right? Moving on. So I told you that there will be one more way by which I'll be able to define my oxidation and reduction, right? So that we'll see now, right? So that particular thing by which I'll be able to give one more definition for oxidation and reduction, other than the three definitions which you already saw, right, is going to be in terms of something called as oxidation number, right? It is oxidation number, right? Please take down the definition for oxidation number, people. Right? Okay. It is the actual charge. It is the actual charge possessed. It is the actual charge possessed by an element in a compound. It is the actual charge possessed by the element in a compound or in an ion. It can be a compound or it can be an ion. Polyatomic ion, definitely. Right? You can even write just instead of just ion, you can write polyatomic. No, just write ion. There can be cases where I can even have monatomic ions. So I'll repeat the definitions, right? So oxidation number is the actual charge possessed by the element in an ion or a compound. Very simple, right? So, or I can even tell that it is the valency of the element. Very, very simple. Most of the cases, right, in 19, like I will say not 19, in almost all the cases, right, you will find that that is basically talking about the valency of the element. But we speak valency in terms of octet rule, right? But you know that octet rule is not the only rule for getting stabilized, right? So I can have species having more than 8 electrons, less than 8 electrons. All these things are possible. That's why I didn't say valency, right? But in some, like in good number of cases, it can also be valency. Okay, right? So going by the definition, right? Going by the definition, you can easily understand what I'm trying to tell you. It is the actual charge possessed by the element, again, by the element, right, in a molecule or an ion. Very, very simple, right? Fine. Now, how are we going to calculate this? How are we going to calculate the oxidation number, right? Okay. Now, there are some certain ground rules which you have to follow for doing oxidation number, right? So the first one is, right, if you find elements in their free state. Okay, what do you mean by free state? Any idea?
Naturally occurring state.
Correct. So how do you see it in nature? How is it naturally available? So if you find that particular element in that state, right, the oxidation number of that element is 0. For example, if you find H2, Cl2, O2, sodium, just sodium, zinc, magnesium, all these things, if you just see them in their natural states or say free states, right? These are what are called as free states, right? So if you find elements in their free states, the oxidation number is definitely 0, right? The oxidation number is 0, okay? So please don't put, if you find Cl2, don't put the oxidation number as -1, no, right? If you see that in a compound, say chlorine is in a compound, NaCl, HCl, in those compounds, yes, chlorine will have -1. That is different, right? So the first point is, if you find elements in their free states, right, the oxidation number of those elements will definitely be 0. Okay, right? Next, right? When I talk about hydrogen, like there are certain elements which you can always predict. These will only be the oxidation numbers, like they will be able to predict. Okay, so what and all we'll see, right? So if I take hydrogen, right? If I take hydrogen, right? Hydrogen can exist only in 2 oxidation states. Obviously, it can be in 0. I'm not talking about that. Other than 0, right? It can be available in 2 oxidation states. See, when I say oxidation number or oxidation state, it is same, right? You can even take it down here. It's oxidation number. It's called oxidation state. Okay, fine. So hydrogen I'm speaking about. So I told you hydrogen can exist in 2 oxidation states, or it can have 2 oxidation numbers. So it will be generally +1 or -1. It will be generally +1 or -1. Now it depends. When will it have +1? When will it have -1? Depends on which other element is there in the compound, right? Which other element is there in the compound, right? So if you find, right, hydrogen is attached to a highly electronegative element, definitely the electronegative element will have the negative charge, right? And obviously hydrogen in this case is more electropositive. So definitely in that case, hydrogen will have a positive charge of +1. For example, ammonia, right? Say HCl, HF, H2O, right? In all these cases, right? You see what is happening here. Hydrogen attached to a highly electronegative element like nitrogen, fluorine, oxygen. All these are highly electronegative elements. So definitely those elements will have negative charge, no doubt about it, right? So in that case, hydrogen will have a positive charge of +1. Okay, fine. Next, when I talk about -1, and obviously it's going to be opposite. If you find that hydrogen is attached to a highly electropositive element, right? Highly electropositive element, in that case, hydrogen is going to have a negative charge of -1, right? So generally this you will be finding in something called as hydrides, right? Hydrides are basically with the ion, hydride ion is basically H minus, right? So what can be examples? So you have so many hydrides, NaH, KH, right? Right? So I have so many examples like this. This is my sodium hydride, this is my potassium hydride, right? So in this case, you see that our sodium is attached to a highly electropositive element, right? So in those cases, you will find hydrogen is going to have a negative charge of -1, or say the oxidation number of hydrogen there is -1, right? So these two are the only possible oxidation states for hydrogen. Okay, so the moment you see a molecule and if you see hydrogen there, depending on what other element is present, you will be able to easily pick what will be the oxidation number of hydrogen in that particular molecule. Okay, so that is about oxidation. Next, we'll move on. Right. Now again, now there are other things also you will be able to predict easily. The moment you see group 1 elements, or group 1 elements, lithium, sodium, potassium, cesium, francium, rubidium. Okay. So if you, the moment you see group 2 elements, right? So the moment you see them, I can easily say that what will be the oxidation number?
1.
Exactly, right? So they have one valence electron, all of them, though they'll easily lose one electron to form a charge of +1, right? So the moment you see group 1 elements, no doubt about it, there is only one oxidation state possible, and that will always be +1. Okay, right, cool. Next, when I go to group 2, what will be the oxidation number?
+2.
Exactly, right? So, you know, beryllium, magnesium, calcium, strontium, barium, right? All these elements have 2 valence electrons. There is no other choice than for these elements to lose those 2 electrons. So obviously the oxidation number of group 2 elements, if you see, will always be +2. Okay, right? Fine. Now for other groups, we'll not be able to predict like this. Okay, why? Because one single element can show multiple oxidation states. Okay, one single element can form multiple oxidation states. For example, right? For example, if I take PCl5 and PCl3, right? So I will tell that phosphorus in both these cases are actually having different oxidation states or oxidation numbers, right? So like now I'll tell you the answer, but I'll tell you how to calculate also, but don't worry, but I'll tell that in this case it is +3, in this case it is +5, right? So only for group 1, group 2 we'll be able to say, okay, this is the only oxidation number available, right? For other group elements, we will not be able to predict the oxidation number, we have to calculate it. I'll tell you how to calculate it, don't worry. Okay, fine. For hydrogen, group 1, group 2, we have predicted. Okay, so next one. When I talk about oxygen, now oxygen can form actually 3 oxidation states, right? Oxygen can form 3 oxidation states, and mostly 90%, right? Obviously, if it is O2, it is 0, no doubt about it. Other than that, right, 90% of times you will see that oxygen is going to be in its -2 oxidation state. We already know it, isn't it? O2 minus. I know oxygen is having 6 valence electrons, right? So obviously it requires 2 more electrons to satisfy its octet. So 99% you will see that oxygen is going, 90% you will see that oxygen is going to have a oxidation number of -2, right? So definitely you will find -2 in generally called as oxides. Oxides, sodium oxide, magnesium oxide, calcium oxide. All these things you'll see that oxygen is going to have a negative charge, or say oxidation number of -2. Okay, fine. Now there are special cases. There are special cases where you can have oxygen to have a -1 charge also, or say -1 as its oxidation number also, right? Now these are what are called as peroxides. Any example can you give me? Peroxides?
So like hydrogen peroxide.
Exactly. That's what I was expecting, right? So you have this compound H2O2, right? Now, how will you understand, right? How will you understand just by looking at the molecule? It's pretty difficult to understand whether it's a peroxide or a normal oxide, right? You have to know the structure. Okay, you have to know the structure of the molecule. Okay, so if you look at this structure, it will be like this. This is how it is going to look. Okay, H2O2, right? So generally what will you see is oxygen and oxygen bond, if you have, right, it will generally be a double bond. O double bond O will only be there, right? But what you see here, I have an O single bond O, right? So the moment you see this O single bond O, not only here, in any structure for that matter, right? So this is what is called as my peroxide linkage. What do you mean by peroxide linkage? O single bond linkage is what is called as your peroxide linkage, right? So the moment you see peroxide linkage, oxygen is going to have an oxidation number of -1. Both the oxygen atoms will have -1 and -1. Okay, so that is the second type of oxidation state possible, right? But again, yes.
I got disconnected for a brief moment, sir. Can you explain the oxide -2 one alone?
Yeah, sure. So what I'm telling is the moment you see like normal oxides, right? Say when you have sodium oxide, magnesium oxide, calcium oxide, or aluminum oxide, all these things if you see. But the moment you see the term oxides, I'm going to have -2 as the oxidation number for oxygen in that particular molecule, right?
Okay, sir.
And that will work for majority of the cases. Majority of the cases, you will find that oxygen is actually going to be in -2 oxidation state, right? And there are very, very few compounds in which you can see this peroxide linkages. In that case, oxygen atom will have an oxidation number of -1. Okay,
sir.
Fine. Now, moving on, there can be one more also, right? There can be one more oxidation number possible for oxygen. Okay, if you've taken this down, I can rub it off. Right. So the other possibility is -12, right? -12. Okay. So again, this is very, very rare. Okay, oxygen to have this -12 is very, very rare. But again, with the compound still, like the molecules still exist, right? So these, so oxides, peroxides. Now -12, if we have, it is going to be called as superoxides. Right, normal oxides -2, peroxides -1, superoxides will have -2. Okay, so how examples can be? It can be say KO2, right? Now KO2, if you check, right? So like I'll tell you how to calculate also. It's very simple, right? So I know potassium is going to have +1 charge because I know the group. The moment you see group 1 element, I know it is going to be +1. Correct. Now I have 2 oxygen atoms, right? And for 2, say I want to find the oxidation number for oxygen. Let me keep it as X, right? Say I have 2 oxygen atoms each having an oxidation number of X, right? Now this is the charge possessed by potassium, and 2X is the charge possessed by oxygen, right? Now the total molecule, if you check, total molecule is actually neutral. right? So if I sum up the individual oxidation numbers or individual charges possessed by the elements in the compound, it should be equal to the total charge possessed by the molecule, right? And in this case, the total charge is 0, right? So you will find that X will actually be minus,
minus 1 by 2.
right? So minus 1 by 2 or minus half, right? So this compound exists, right? So when I go for your inorganic chemistry, so you'll find you have here group 1 elements and group 2 elements, alkali and alkaline earth metals. So in that we'll talk in depth what happens here. Okay. So now you have to understand that the moment you see superoxides, right, you will find that their oxidation number will be minus half. That's what you need to know. Okay, right. Now, there can be exceptions for this. I mean, I told you that there are only 3 things possible for oxygen, but there is only one compound in whole of chemistry. There is only one compound in all of the chemistry where oxygen is going to have a net positive oxidation number. Right? Generally, what happens? Oxygen is one of the most electronegative elements in the periodic table, right? So you will find oxygen generally to have only negative oxidation states, right? But there is only one compound, one and only one compound, where oxygen can exist in positive oxidation state. Can you tell me which will be the other element which will be present there in that compound where oxygen is having a positive oxidation state?
More electronegative than oxygen.
Oh, which is that?
Fluorine.
Fluorine.
Exactly, right? So the moment you see oxygen combining with fluorine, right? Yes, I am going to have a positive oxidation state, right? And there is only one compound, right? So it can have an oxidation number of +2. There is a compound called as OF2, oxyfluoride, right? So in this case, definitely fluorine is more electronegative than oxygen, right? So definitely it is going to have a -1 oxidation state. So oxygen is going to have a +2 oxidation state. This is the only compound. There's no other doubt, right? Yeah, I can have this compound O2F2 also, fine. If I consider O2F2, this will have +1, right? But again, you will not be asked questions from O2F2 because the O2F2 compound is highly unstable, right? But yeah, OF2, a good number, like a good, highly little stable compound, right? So +2 and +1, the moment you see oxygen coming with other elements, say a more electronegative element than oxygen, that the only element possible is fluorine, right? So the moment you see oxygen with fluorine, you can say that oxygen is going to have a positive oxidation state. In OF2, it's +2, and in O2F2, it is +1. Okay, right? Good. Yes. So moving on. So that's about. Yeah. Tell me, Kanna.
Sir, O2F2 is a peroxide, no, sir. It has O linkage.
Correct. It is a peroxide linkage, but why I didn't call it as peroxide linkage? Because it should have -1 oxidation state. Now here it is having.
So this is exception, sir, in peroxide.
Yes, this is an exception. This is the one and only molecule.
Okay, sir.
You can call it as peroxide if you want, but ideally speaking, peroxides should have -1 oxidation state for oxygen. That's why I didn't call it as peroxide here.
Okay.
Nice doubt, right? Okay, moving on. Right. Now, next element which you're going to speak is about fluorine. Again, there is no other oxidation number available other than
-1.
Yes. Moment you see fluorine, there is no other oxidation number possible because it is the most electronegative element, right? So fluorine will definitely have only one oxidation number of -1, whatever the compound is. 0 in F2, and in your compounds it is going to be -1, no doubt. Okay, moving on. Any other thing which I can specify? Yeah. So yes, people. So other than these elements, other than these kind of whatever I gave you, right? You have to calculate it, right? For all the other elements, there is no other way than to calculate it. Okay, fine. Now, how are we going to calculate it, right? So the first thing you have to know is say, I'll just give it as a point itself, right? So the thing which you have to know is, if I add all the oxidation numbers of all the elements present in a compound, right? So the total oxidation number of all these elements should be equal to the overall charge possessed by the molecule. I'll write it in simple words. The sum of oxidation numbers in a compound or in an ion or whatever it is, right? The sum of oxidation numbers should be equal to the overall charge of the molecule, right? Should be equal to the overall charge possessed by the molecule. Okay, right? So keep this in mind, right? And there can be cases, right? There can be cases where how to put it. Actually, we'll not see it now. Like you can see it. Okay, what I was about to tell you is, you can see cases where the oxidation number is going to be actually decimal, or say it can be like 1.666 or say 2.333, something like that, right? So the moment you see all those things, right, you have to understand that there is something not wrong. There is something extra information which you have to know. Okay, so that we'll not see it now. Okay, so these are all the things which you have to know, people, right? So these are all the things which you have to know regarding your oxidation number. Now we'll take directly examples and go for the calculation. Okay, fine. Let me start with a simple example, right? So let me take H2SO4. Okay, so in H2SO4, I have to calculate what is the oxidation number of sulfur. Can you calculate and tell me? Right, so fine, this I will do. It is going to be +6. Okay, correct, right? So this I will do, right? Fine. So I know the moment I see hydrogen, right, and that too you see that it is attached with more electronegative elements, that is sulfur and oxygen. Definitely hydrogen is going to have a positive charge of +1, or say the oxidation number of hydrogen in this molecule is +1, right? Now please don't forget to put the number of such atoms present. If you are not going to put that, the entire calculation is wrong, right? So please understand that there are 2 hydrogen atoms each having a oxidation number of +1. So that has to be included in the calculations, right? So I have 2 hydrogen atoms each having an oxidation number of +1, right? And for sulfur, I have to calculate there is only 1 sulfur, so I'll put it as 1x or just x, right? And for oxygen atom, I know it is a normal oxide, there is no doubt, right? So I'm going to have a charge of -2, or say oxidation number of -2, and there are 4 such oxygen atoms having an oxidation number of -2. So I will write it like this: 4 into -2, right? So now I told you that the sum of all the oxidation numbers should be equal to the overall charge possessed by the molecule, right? So what is the overall charge here? This compound is neutral. There is no charge on this. So I can say that it is going to be 0. Right? So now I can easily calculate your x. X, if you calculate, you will find that sulfur is in +6 oxidation state. Okay, right? So this is one example. Okay, fine. So next, I'll just take this one, HNO3. I want to calculate for nitrogen. Can you calculate?
Five, sir.
5, sir.
Yeah, it is going to be 5. So again, the moment you see hydrogen, more electronegative element, +1, and there is only 1 hydrogen in this, so +1, and nitrogen I have to calculate, so let me keep it as x, right? And there are 3 oxygen atoms. Obviously it is going to have oxidation number of -2, right? So I have +3 into -2, right? So obviously you will find that it is going to be +5. Okay, One more example. I have MnO4 minus. I want to calculate what will be the oxidation number for manganese. Go for it.
Seven, sir.
Yeah, it is 7, right? So again, for manganese, I'll keep it as X. This is what I want to calculate, right? Now I have 4 oxygen atom each having -2. Now please understand, in this case, it is not equal to 0. It should be equal to the overall charge possessed by the molecule or an ion. And obviously here in this case, it is -1. So this should be equal to -1, not 0. Please, 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 please understand, right? Okay, so obviously if you calculate, X will be in +7 oxidation state. That is, manganese is in +7 oxidation state. Okay, let me take one more example. Let me see if you're smart enough to answer this question. I have NH4NO3, ammonium nitrates. I want to calculate what will be the oxidation number for nitrogen. Go for it.
+1, sir.
+1. Okay. Any other answers?
Even I got +1, sir.
Okay, people. Right. So the thing is, I know how you would have calculated. You see that there are 2 nitrogen atoms, so 2x, right? And there are 4 hydrogen atoms, so each having +1, right? And I have 3 oxygen atoms, each having -2, so totally equal to 0, right? So you'll find that 2x plus 4 minus 6, yeah. So you'll find x as +1, right? Absolutely wrong. Now, what is happening here is you really need to understand what are all the ions present here. Okay. Now, please understand here, I will be able to write this molecule as NH4 plus, and I have NO3 minus. This is how you write this molecule, right? So, nitrogen here will have one oxidation state, and nitrogen here will have another oxidation state. You cannot calculate it like this. It's an ammonium ion, and I have a nitrate ion. So definitely you have oxygen to be more electronegative here. So nitrogen will have a positive oxidation state. And in this case, it is attached with hydrogen. So definitely in this case, it is going to have a negative oxidation state. Okay, so you have to be very careful in these kind of questions. Okay, the moment you see this kind of an ion, this kind of a molecule, you have to know that it is basically an ionic compound in which I have an ammonium ion and a nitrate ion. So definitely you have to calculate the nitrogen's oxidation number in 2 different cases. One in this, one in that. Go for it. In both the cases, you tell me what will be the oxidation number. Yes, answers?
So I got for NH4 plus NSC oxidation state is -3, sir.
Yes,
Oh,
correct. So
And then for NO3 minus, it's 5.
+5, right? Okay, correct. So here let me calculate. So I have X for nitrogen, and I have 4 hydrogens each having +1. The total charge is +1. Again, please don't forget to put +1. Please do not put a 0. Okay. So if you calculate, X will be -2. No problem. Okay, now going here, X is the oxidation number for nitrogen, and I have 3 oxygen atoms each having -2 as the oxidation state, right? So you will find, and obviously equal to -1. Total charge here is -1. So you will find the oxidation number to be
+5.
Okay, now I will actually be able to relate these 2 numbers with the number which I got. That is, when you did it wrong, right? You got +1 as the oxidation state. Now, how are you getting it? It's very simple. It is basically, I have two nitrogens having two different oxidation numbers. So if I take the average of these two, what do you mean by average? So I have +5 as one number and I have -3 as another number. How many such nitrogen atoms are there? There are two nitrogen atoms. So you will count as +1. This is how you are getting +1, right? This is the average oxidation number for nitrogen in this molecule, right? So the actual oxidation number should be calculated in this way, right? So whatever you found there, when you're, sorry?
Why you took X plus 4, sir?
X plus 4, okay, there are 4 hydrogen atoms, each having a charge of +1. Understood?
Yes, sir.
Okay. So what you found here when you calculated is actually the average oxidation number. Okay, fine. Let me go for another examples. Okay, so let me take Fe2O3. Calculate the oxidation number for iron. Go for it. Oh, sorry, not Fe2O3. Sorry, it is Fe3O4. Okay, it's Fe3O4. Now calculate for iron, Fe.
12, sir.
12?
8 by 3.
2 by 3, sir.
Okay, you're getting 8 by 3. I told you. So whenever you have this fractional or decimal values, you have to know some extra information. Okay. So we'll see what is happening here. So let me calculate it by the normal way. So I have 3x. So I have 3 iron atoms, each having x, right? And I have oxygen atom, 4 oxygen atom, each having -2, which is equal to 0. So yes, you expect the answer to be 8 by 3. Okay. So again, the moment you see fractional oxidation states, just like the previous case, it is actually going to be the average oxidation state of iron. That means, just like how you saw nitrogen is existing in different oxidation states, in Fe3O4 also, iron is actually existing in 2 different oxidation states. Okay. Now, how will I know it? It's very simple. Now, this compound, I will be able to write it as Fe3O4. I'll be able to write it as FeO plus Fe2O3. Look at this, right? FeO, again 1 plus 2, 3, 1 plus 3 will become 4. So it will become Fe3O4, right? So this is what is called as ferroferric oxide, Fe3O4. The name of the compound is called ferroferric oxide. Right. So I know iron can exist in 2 oxidation states, +2 and +3. Right. So when I have +2, it is called ferric or ferro, whatever it is, and the other one is going to be called as ferrous. Ferric, ferrous. Ferric is for +2, ferrous is for +3. Okay. So these kind of oxides are what are called as mixed oxides. Right? So these kind of oxides are what are called as mixed oxides. So what do you mean mixed oxides? Mixed oxide is an oxide where the metal exists in 2 or more oxidation states, just like this. Right? The element exists in 2 or more oxidation states. Right? So here for ferroferric oxide, that is Fe3O4, and I easily understand that in this case, if I calculate for FeO, what will be the oxidation state of iron? Can I say it is +2? How will you calculate? X minus 2 is equal to 0, so X is +2. Got it, right? For here, I have 2X plus 3 into -2 is equal to 0, correct? I have 3 oxygen atom having -2, so you'll find X to be +3. No problem. Okay, so you have +2 and +3 simultaneously existing in this molecule, Fe3O4. right? Now again, I'll be able to connect what is this 8 by 3 with this, right? Now it's very simple. There is one iron atom. There is one iron atom which is having a charge of +2, right? And there are two iron atoms which are having a charge of, or say the oxidation number of +3. So 2 into +3. Totally how many iron atoms? 3 iron atoms. 8 by 3. Right? So the moment you see fractional oxidation states, people, right, you have to understand that that is not the exact answer. That is actually going to be the average oxidation state present for that particular element, right? So you have to understand that there are going to be two different oxidation states, and for each of these oxidation states, you have to calculate the oxidation numbers. Understood, right? Okay, fine. Now, any other peculiar example I can give you? Yes, I can give you. Right. Now, if I want to calculate CrO5, I want to calculate it for chromium. Okay. Right. I want to calculate it for chromium. So if you calculate, you will find it as plus 5 into -2 is equal to 0. So x is +10. Correct? Right? I'll find x as +10. Oh. So what do you mean by this? If I say chromium is having a charge of +10, what do you mean by that?
It's more than the valence in octet.
So basically what I'm telling is it has lost 10 electrons. That's what we need to understand. Never, ever possible. Right? So there are, okay, the maximum oxidation number in all of the periodic table, in all the elements, I have almost like 118 elements, right? So the maximum oxidation number till now, which we have found out, is +8, right? Till now, what you have found out is +8. More than that, it is never possible, right? That means here something is happening, okay? So here something is happening. So now I tell you what is that particular compound in which I can have +8 oxidation state. There is an element called as osmium, OS. Okay. So when this combines with oxygen, I form OSO4, osmium tetroxide. Okay. So in this case, if you calculate, obviously you will find that osmium is going to have a oxidation number of +8, right? So again, this compound itself is not that stable. Okay, so the maximum oxidation state you can ever see in a compound for a particular element is +8. So definitely this calculation, what I did here is wrong. There is some problem. Okay, so what happens here, we'll see. Why is it that I'm getting +8? Is because I'm doing something wrong. So we'll see what is the right thing which we have to do. Okay. So what happens is for the okay, you don't have to, sir. If I give you the answer, you will ask me, sir, how will I know all this? Do not worry. These are very, let's say, exceptional cases for which only you will be asked. So the thing is, the answer to this question lies in the structure of the molecule. Okay. So if you look at the structure of the molecule, it is going to be like this. CrO5 will actually look like this. This is how it looks. This structure is a very famous structure called as butterfly structure. Right? This structure looks like a butterfly, isn't it? Right? So this structure is famously called as the butterfly structure. Okay. So here you cannot take for all the oxygen atom, it is going to have -2. No. Right? So what do you see here? In this compound.
There is a linkage between oxygen and
Double bond.
What is that? What is that linkage called as?
peroxide.
Peroxide.
Correct. So you're seeing that there is a peroxide, two peroxide linkages here, right? So obviously for these two oxygen atom, it is actually going to be -1. Again, for these two, it is going to be -1. And for this oxygen atom, no doubt it is going to be -2. Right? So for 4 of the oxygen atom, you have -1. For 1 of the oxygen atom, you have -2. right? So now how will I calculate for Cr? Let me keep it as X, right? Plus there are 4 oxygen atom having -1, that is peroxide linkages, and there is 1 oxygen atom having -2, which is equal to 0. So you'll find X as +6. So chromium here exists in +6 oxidation state. Okay, right? So don't worry, so sir, don't ask me how will I know the structures, how will I know all this, how will I know that oxygen is existing peroxide form? Don't worry, right? So these are some some very special cases, only from which you'll be from this questions can come out, but might not come, right? But if it is asked CrO5, now you'll remember it is going to have a butterfly structure. The thing about chemistry is, people, right? Like in physics, right? You know, you have proper logical explanations for all of them. Here also I have logical explanation, but if I give you the explanation, it is beyond the scope of 11th. Okay. You know, you have formulas in physics, so you'll just apply the formulas or apply the concepts wherever it is, and you'll get the answer. But here in chemistry, there's a lot of remembering to do, right? And it is not going to come in one day. It will come as you practice more and more and more, as you see more and more amount of peculiar compounds, strange compounds like this, right? You will eventually get the grasp of it. So don't worry. Okay, fine. So that's about one peculiar compound. Okay, let me take something like this again. I will take, let me take, okay. See, I'm not trying to scare you with the compounds here, but I'm just telling you that this is also possible. Okay. Right. So let me take H2SO5, not H2SO4. Right. So I have H2SO5. Right. So again, if I calculate it for sulfur, let me calculate. So you will have +2. Okay, I'll write like this: 2 into +1 plus X for sulfur plus 5 into -2 is equal to 0. Right. So what will you find is X? X is going to be in +8 oxidation state. Again, not possible. Right. +8, if you calculate for sulfur, that too is never ever possible. Right. So you can see that +6, +7, not +6 is possible for sulfur, but more than that, +7, +8, and all these things are possible only in D and F block elements. That is your transition elements. Between S and P block, you have some elements in between. Correct? You study about them in your 12th class, but only in those cases you can have these kind of oxidation states, +8. Okay. So now again, something is wrong. I have to look at the structure. Okay. So if you look at the structure, it is going to be like this. I have sulfur to have 2 double bond O's. I have an OH, and I have a peroxide linkage again. Right? So again, what will you see? There are going to be 3 oxygen atoms which are going to have -2. Which 3? This one, -2, -2, -2. For all these 3 high oxygen atom, I'm going to have -2. Right? And obviously for these 2 oxygen atom, I'm going to have -1 and -1. Right? So now I can easily calculate what will be the oxidation number. Fine. So let me, for 2 hydrogens, it is 2 into +1. Right? And let me keep it as X for sulfur. Right? Plus I have 3 oxygen atoms having -2. Right? And I have 2 oxygen atoms having -1. And the overall charge is 0, right? So now I have 3 into 2 is +6 plus, okay, -6, -8 plus 2. So X is +6, right? So again, this all will come with practice. Okay, so H2SO5 is another compound like this. Okay. I can actually complicate it more and more, but I really don't want to scare you. Right? That's why I'm not doing this. Okay, this chapter has already started in your school, isn't it? Guys?
Yes, sir.
Okay. So what now you learned there in oxidation numbers? Did you see all these compounds already there? Did you see this fractional oxidation numbers when I have this peroxide linkages? All this, did you see in your
school,
school?
sir.
In school.
We saw some cases having like this.
Okay. I think it was.
I don't think we saw the structure and
Yes,
structure
sir.
you didn't see. Okay. Okay.
we just left it in the fractional form.
Oh, they just left it in the fraction.
Sir?
They just left it in the fraction.
That's what I think, sir. They did.
Okay. Okay. Fine. Let us see. There are only 2-3 more examples like this peculiar oxidation numbers. Okay. So let me go for it. Okay. I'm sorry. Did you take down the structures, people?
Yes,
The
sir.
structure was copied.
Yes,
Okay.
sir.
Okay. Okay. So let me take H2S2OH. Right? H2S2OH. Okay. So again, the moment you see this kind of complex molecules, you have to know the structure, people. Like if not, you will not be able to answer the questions. Like answer what will be the oxidation numbers. Okay. So let me give you the structure. This is how the structure looks. I have S double bond O, another S having double bond O. Okay. Now let me give you some tricks here. Okay. So the thing is, the moment you see hydrogen atoms in this kind of, these are what are called as oxy acids of sulfur, right? Oxy acids of sulfur. That means I'm going to have sulfur, oxygen, and I'm going to have hydrogen, and definitely they're going to behave as acids. Okay. So the thing is, the moment you see sulfur, right? Sulfur and oxygen can have a double. Generally, if you have a bond between sulfur and oxygen, it will generally be a double bond, right? Or will not even go into it. You have 2 hydrogen atoms, right? You have 2 hydrogen atoms, and please understand that the hydrogen atoms will be able to come out as H plus. That is, it can behave as an acid only if that hydrogen is attached to oxygen atom. Right? That hydrogen atom is attached to the oxygen atom. So, like if not, if you find that that hydrogen atom is directly attached to sulfur, it cannot behave as acids. Okay. So you have 2 hydrogen atoms which are going to come out as H plus. So definitely you need to have you need to have 2 OH bonds so that it will be able to come out as H plus. So definitely I'm going to have 1 OH bond this side, another OH bond this side. Done. Okay. Anything? Oh, yeah. So how many oxygen atoms over? 1, 2, 3, 1, 2, 3, 6 are over. Right? Now, there are 2 more oxygen atoms. How can you connect them, people?
With the sulfur one. One with sulfur and one oxygen linkage. Peroxide linkage.
Exactly. Right. So you will have this kind of structure. Right? So you can connect these 2 sulfur atoms by having a peroxide linkage. Right? So again, I know all 6 oxygen atoms here are going to have -2, right? And these 2 are going to have -1 and -1. Okay. So now you can easily calculate what will be the oxidation number for sulfur, right? So for this, if I calculate, you don't even have to go for the calculation. You can easily see it how it is happening. -2, -2, -2, -6. Okay, we'll calculate actually. Yeah, it will again, we're going to be +6, right? We can actually calculate, right? So I have 2 hydrogen atoms having +1. There are 2 sulfur atoms, so 2x. And out of the 8 oxygen atoms, 6 of them are having -2, and 2 of them are having -1, right? So you'll easily calculate x to be +6, right? So +6 will be the oxidation state. Okay. You will study all this again in your 12th class, right? You will study all these structures in your P block elements, right? You have group 14, 15, 16, 17, 18. So in those times, you'll be studying about these. Don't worry again. Okay. So there is 2 more, and then we'll wind it up. Wait, if there is no more oxidation numbers. Okay, take down the structure first. Okay, so the compound which I'm going to see is Na2S4O6. Na2S4O6. Now, this is again a very, very peculiar compound because you are going to find something which you didn't find till now. Okay, let me give you the structure. Okay, or let me write it as S4O6 2 minus. I just removed the NS. Okay, sodiums I've removed. So I'll write it as S4O6 2 minus. Okay, fine. So let me do it. So I have 4 sulfur atoms here, right? Let me write the 4 sulfur atoms. Okay, so now the first and the last, I'm going to have 2 double bonds. Okay, and you see that there are going to be 2 negative charges. Definitely those 2 negative charges are going to be possessed by oxygen, right? So I can easily put one more on both sides, O minus, and another O minus. Done, and that's it. Connect all of them. That's it. Okay. So now you are finding a very new kind of linkage. Look at this, right? Now this is going to be called as a per-sulfide link. Okay, this is not per-sulfide linkage. I'm sorry. No. Right. So why am I not calling it? So generally, if you find S double bond S, right? So I'll call it. I mean S single bond S. I will call it as per-sulfate linkage, but this time I will not call it because there are already 2 more sulfur atoms like in this side and that side. Okay, so this is equivalent, right? This 1, 2, 3, 4, I will be able to write this equivalently as S double bond S. Okay, S double bond S. So obviously I know for these 2 sulfur atoms, the oxidation number is 0 because I will be able to regard them as S double bond S, and sulfur is, S double bond S is the free state for sulfur, right? So it is going to have 0. Okay, so for these 2 sulfur atoms alone, I'm going to have 0, right? And for other 2, it's going to be, there's going to be some oxidation number. Okay, now easily I can say what will be the oxidation number, -2, and oxygen is having -1. Already it's given, the charge is given, so it's -1. So you will find for both the sulfur atoms, here it is going to be +5 as the oxidation number. Okay, so don't worry about all this. 99% you will not get questions from this. Okay, normally they will ask you to calculate just the oxidation number of normal compounds. Okay, and oxidation numbers are not, like, basically the application of oxidation number is what is important, right? So you will find that I told you that you will be able to, oh yeah, that's about oxidation number, people, and you will be able to find or define oxidation number, you'll be able to define oxidation or reduction in terms of these oxidation numbers, right? And one more thing what you'll be able to do is that with the help of these oxidation numbers, you will be able to balance the chemical reaction, right? You will be able to balance the chemical reaction. So these 2 are the applications point of view, right? First, time is 8:16. I'm really sorry, right? So I'll just quickly wind it up. So thing is, you'll be able to define what is oxidation and reduction in terms of oxidation number, as well as you'll be able to calculate what, not calculate, you'll be able to balance the chemical reaction. So that we'll see next class, people. I am really sorry I didn't see the time. Please go to your schools. Go for the online classes. We'll see you again. Bye-bye. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you.